Hello, class. This is Mr. Hart, and in this podcast, we want to talk about the last part of the electromagnetism unit, and that is about what we call the current wars. Okay, and this lesson is really fun because it kind of gives you a historical perspective of what was involved in getting electricity into our homes. Okay, when you plug into an outlet, you probably take for granted that you have electricity, and we use it every day. But there was a lot of politics and things like that were involved in what type of current we used. A lot of propaganda schemes and things like that. So it's kind of a really cool historical lesson. So let's kind of get into it. But first of all, let's talk about what the two types of currents are and why they were being debated about so much. Okay. So the two types of currents are what we call direct current and alternating current. Okay. And direct current is just a flow of electrons that travels in one direction down a wire. And then alternating current is the flow of electrons, but they just alternate and switch back and forth quickly through the wire. Okay, so let's kind of look at why one might have an advantage compared to the other. Okay, so for example, let's just say we make a very basic circuit. Okay, we have a power source. Okay, it goes to, let's say, just like a light bulb. Okay, that's our light bulb, and then back to the power source. On direct current, okay, that electron, okay, is flowing through this circuit. It's going to go through the circuit to the light bulb, go all the way back to the power source, and so on. Okay, it flows through the entire circuit in that loop. Okay, now that's nice. It's simple to think about. That's how batteries work. Okay, but it's not very efficient because that electron, once it has powered the light bulb or whatever it is, it has to go through the entire circuit, and that gives away a lot of energy and creates a lot of heat. Okay, so it's not as energy efficient. Okay, comparing that to alternating current, okay, let's draw the same thing down here. Okay, and I know my drawing's not great, but you get the point. So circuit, light bulb, power source, okay. Now, instead of trying to push all the electrons through this circuit, okay, now we just have a couple set of electrons, okay, and what they're going to do is they're going to power that light bulb. They're going to go through the light bulb like that, but then once they're done going through, the circuit alternates, and then they'll go back through the other direction and back through the other direction. They'll just go back and forth and alternate through the circuit. So just constantly in the same position, just going back and forth, back and forth, back and forth. Okay, that's a lot more energy efficient because instead of having to push all those electrons through, they just have to go through a smaller space. Okay, so it doesn't lose as much heat. It's a lot better for energy transfer and things like that. Okay. So fortunately, we do have alternating current in our homes. When you plug into a standard outlet, you have alternating current. It's much more efficient, okay? But it wasn't always that way, believe it or not, okay? And this is where the current wars come in, okay? In class, we watch a documentary called Mad Electricity by Modern Marvels, okay? And it's an awesome documentary. It talks about these current wars, okay? And the current wars is kind of this moment in time between these two guys right here. This guy right here you may recognize as Nikola Tesla, okay? And this guy on the right, probably don't recognize him as much because he's a little bit older, but this is Edison, Thomas Edison, okay? And so the current wars was between these two guys right here, okay? Nikola Tesla was a big proponent of AC current, okay? And Thomas Edison was a big proponent of DC, okay? Now, let's talk about why the current war starts. So keep in mind, Edison's about 30 years older than Nikola Tesla. Okay, Edison invents the light bulb when he's young, does all these great things with electricity, comes up with a lot of inventions. He's kind of this, scientific hero. Okay, does a lot of great things for electricity. Okay, but because he was so famous, he starts to become kind of this rich businessman. And when he gets older, he's kind of done with inventing, and now he's just kind of focused on making money. He's kind of this very, prudent businessman, kind of mean, and, does whatever he needs to get the job done type thing. Okay. Nikola Tesla is kind of this poor boy from Croatia, but very intelligent. He gets a note from a friend telling Thomas Edison that he recommends hiring Nikola Tesla, and that's how Nikola Tesla gets his first job in the United States. Okay. Tesla's working for Edison, does all these amazing patents, and Edison had promised Tesla a bonus if you'd invent these things, but in the end Edison doesn't pay him that bonus. Okay, kind of just says I was just joking. You need to understand an American sense of humor, that type of thing. Okay, So Edison's just kind of this cutthroat businessman. Tesla's working for him, doing all these amazing things for him, and then he just kind of kicks Tesla to the side type thing. So ever since then, they're just kind of these bitter rivals, okay? And Tesla, in his youth wasn't as famous, but he understood that AC had a lot of advantages compared to DC, okay? But Edison had already kind of developed this DC infrastructure in New York and kind of the early foundations of electricity, and so he didn't want to switch. He didn't want to lose his money if they switched to AC and, all these different things. And so there's just a lot of, political things that happened. Edison would electrocute elephants with AC current to show how dangerous it was, that you didn't want in your home, and that type of thing, okay? And so that's what we call the current wars. Thank heavens, though, Tesla eventually gets a contract to work the Chicago World's Fair, okay? He lights up the entire World's Fair with AC current, and after that, he gets the contract to build a dam on Niagara Falls, or not Niagara Falls, but part of Niagara Falls, and light up Buffalo or give electricity to Buffalo in New York. And so after all these things, Tesla basically gets the win. We end up with AC current, okay? The Westinghouse Corporation helped him a lot in getting kind of this structure built up, and we have AC current today. And thank heavens we do. All right, so that's a little bit about the current wars. Let's talk about why it's so important that we have AC current and not DC current, okay? Let's look at the pros and cons, okay? So back then, okay, there was an infrastructure for DC current. Let's just talk about some of the pros and cons of DC current, okay? One pro back then of why they used DC current and why they started with it was because it was simple to understand, okay? Think of like a battery circuit. You have a positive end, you have a negative end, you put the wire through, and you got a circuit, right? Electron flows in one direction. Not a whole lot of things to think about. It was easy to think about, easy to set up, okay? But it's not very energy efficient, so there's a lot of heat loss. Okay, that's a major con. Okay, and here's the big one, and this is why I always say, thank heavens we don't have this. Okay, for DC current, you can't have multiple homes powered by the same power line. Okay, so if you had, like in New York, for example, back then they had these huge like barrels and tunnels filled with wires because each home needed its own power line directly to it from the station. Nowadays we just kind of branch out in locations. You've probably seen green boxes on the side of the road, things like that. That's where the homes get powered from. It's really easy. With DC current, you'd have to have an individual line to every single home, okay? So just tons of lines that you would need to have, okay? And nowadays, you can imagine with our population and all this, there's no way we could implement a DC structure anymore. It just wouldn't work out, okay? Compare that with AC current, okay? Going back, it's easy to branch out from a single line, right? We can get a main power line that goes to a neighborhood, right? And then from there we can branch out, which is very nice. Makes it a lot easier to implement and structure because, again, you don't have to send all the electrons through one line. They're just going back and forth. So it doesn't really matter where they are on the line as long as it connects to somewhere in the power source, okay? Other pros is it's very efficient for energy transfer compared to DC. Okay, there's still some heat loss, but not nearly as much as there is for DC. So you've probably seen power lines across like the canyon and things like that. Those high voltages work really well. They don't lose a whole lot of energy, okay, because they're AC power lines. Okay. Cons though is back then it obviously wasn't set up yet, and people didn't know how to think about it. The generators were kind of more complex. Tesla's electric motor and generator we kind of talked about in these other lessons really weren't understood very well back then, and so the setup was the main thing. This infrastructure wasn't there. Okay, nowadays we know how to use it. The infrastructure's there, so it's great. That's not a problem anymore. But that's it. That's kind of the comparison between the two back then. Some people are saying we should switch back to DC now, which I think is kind of crazy, but the reason why is because a lot of our computers and stuff run on DC current. If you think about it, if you ever look at your computer power cord, you probably have a big huge block, okay? You have the outlet and then the big huge block, and then it goes to your computer. That big huge block converts the AC current to DC current, okay? So a lot of people are saying, oh, we should switch back to DC current because everything runs on DC now. Well, that's still not the case. Like we were saying, we can't have all these different lines running. So I don't see that happening anytime soon. But the only way that would make a lot of sense is if we had a very solar panel dependent infrastructure, right? Because solar panels actually generate electricity in DC current. And so if we could put solar panels on homes and the homes ran on those solar panels, then it makes sense to run back to DC. But for right now, I don't see that happening anytime soon. AC just makes so much more sense in terms of the efficiency involved, especially in the way our infrastructure is set up where everyone's powered from a central power station. Okay. So anyways, it's good that AC won. We're happy we have it. It took a lot of battling and political arguments and things like that to get to work, but thank heavens we have AC current. So let's talk about one more thing that makes AC current so effective, and that is the transformer. Okay. And a transformer is a device that uses electromagnetic induction to change the voltage on a wire. Okay. This is how we are able to transfer electricity so effectively. Okay. So this is not a transformer. Okay. That's not what we're talking about. Okay. We're talking about a electrical transformer, which looks something like this. Okay. If you go down Provo Canyon, right at the mouth of the canyon, you've probably seen kind of a power station looking thing at the base of the canyon. Those are actually transformer stations, okay? Because if you want to transfer a whole lot of energy, okay, to another location, especially a long distance like through a canyon, it makes sense to step up the voltage. The higher the voltage, the more energy efficient it is, okay? So our standard electricity is at like 120 volts, okay? So when it goes to your home, okay, it's at 120 volts, okay? But that's not the best for transferring the energy. So what they'll do is before it gets through the canyon, at the mouth of the canyon, they'll use a transformer and step it up to like 2,400 volts or something crazy like that. Okay. Now you wouldn't want that in your home. Okay, that could easily electrocute you, and definitely not safe. So that's only for long distance transportation of electricity. So they, through the canyon, there's not a whole lot of homes. No one's going to be using that directly. So they step up the voltage, or they put it through the canyon. Then when it gets to the other side, they bring it back down. Okay, that's why it makes it so easy to move electricity for AC current. Okay, so again, transformer is just a device that uses electromagnetic induction to change the voltage on a wire. Let's look at how it works. Okay, it uses the properties of electromagnetic induction. So basically, it's just one component. There's transformers even inside little circuits on your computer and things like that. Okay, but what you do is you put a current on this wire right here on the left side, or whatever side it is. Okay, and as we learned before, that creates a magnetic field. Okay, well, that magnetic field goes through this iron core. Okay, and as that magnetic field is going through, that causes a current to come on this one. Okay, on this side. So simple principles of electromagnetism, right? But what it does is, because there's more wires on this side, okay, than there is on this side, that magnetic field creates a higher voltage on this side than it does on this side. Okay, so based on the differences in how many wires are looped around on each side, can change the voltage. So if you have 10 times more wires on this side, then you'll have 10 times more voltage on the other side of the transformer. Okay. So a really simple device, but very useful for AC current, because we can easily step the voltage up and down. Okay. All right, let's look at an equation that helps us describe how much the voltage goes up. Okay. So this is our equation. Okay. And basically it just says that if you want to find out the voltage on the other end of a transformer, you just take the number of loops on the second end compared to the first end and times it by the voltage on the first end. Okay. So I'll just call this voltage out. Okay. And this is voltage in. Okay, so you want to figure out how many volts you have on the outside of the transformer, or output of the transformer. Okay. You just take the ratio of the number of loops, okay, like we were looking at. So if there's 10 times more loops on the output than the input, then you'll have 10 times as much voltage. Okay. So it's just a simple ratio. Okay. Not too hard to work with. You just count basically the number of loops on each side, compare them, and then that is how much larger your voltage is, okay, on the output. Okay. Sometimes it can be smaller too. On the other side of the canyon, for example, you have to step down the voltage back down, and so you would just switch it so the transformer has more loops on the input than the output, and you get the voltage to step down. Okay, so the voltage output equals number of loops ratio times the voltage input. Okay, let's just do one quick example problem, and then we'll call it good. Okay. So a transformer has an input voltage of 120 volts. If the input wire loops the core 20 times and the output wire loops the core 60 times, what is the output voltage of the transformer? Okay. So we know a couple things. We know the voltage input. Okay, so that's V1. So that's 120 volts. We know that the number of loops on the input is 20. We know the number of loops on the output is 60. Okay. So we just say voltage 2 equals the number of loops on the output, which is 60, over the number of loops on the input, which is 20, times the voltage, which is 120 volts. Basically, 60 over 20 is 3, meaning there's 3 times more loops. So that just means we're going to have 3 times the amount of voltage. Okay, so that's going to give us 360 volts. Okay, so that transformer will step up the voltage 3 times as much. Okay. And that's it. Simple as that. Alrighty. But hopefully that all made sense. I hope you enjoyed the electromagnetism unit. It's one of my favorite. There was a lot that went into getting electricity in our homes, but hopefully you appreciate it now a little bit more and understand it a little bit more. But hopefully that all made sense. Let me know if you have any questions, and thank you for watching.